A very good morning class 12th students. So this is your subject physics, chapter number 14, that is electronic devices, and this is lecture number 3 of chapter number 14. So in lecture number 2 you studied about extrinsic semiconductors which are impure, and then you came to know about two types of intrinsic semiconductors, out of which about n-type semiconductors we have studied in details. So today we will be starting with P-type semiconductors, and as we studied N-type semiconductors in 4-5 points, similarly we will be studying about P-type semiconductors. So the very first point of P-type semiconductors is that in this trivalent impurity is added. If you remember, in N-type semiconductors we have added pentavalent impurities, but in P-type we will be adding trivalent impurities, that is, which will be having 3 valence electrons, right? For example, aluminium, boron, all these have 3 valence electrons in their outermost orbit, so they can be taken as impurity for P-type semiconductors. So now here again I have taken a germanium crystal and I have added aluminium to it, which will be having, as I told you, 3 valence electrons. Okay, so now if you see what will happen, these 3 valence electrons will form covalent bond with the another germanium atom which is adjacent to aluminium atom, right? But now because this germanium also needs a covalent bond, but because of the absence of an electron here, because all the 3 electrons of aluminium are already used, so here a hole is created, right? Now what happens, this germanium aluminium bond wants to complete itself, so therefore this electron will break, that is, any electron from germanium bond will break, and this will fill the aluminium germanium bond. So this is your B point, an electron move from germanium bond to fill aluminium germanium bond. This I have shown here. When this electron will move here, this hole will be completed, but a hole will come here. So if you see what you can say by these two diagrams, so you can say initially the hole was present here, and after moving of electron, this hole is now present here. That means the holes are moving in this crystal. The position of hole has been changed. So you can say each impurity atom tries to accept 1 electron from crystal, as this has accepted 1 electron. Similarly, each impurity atom will try to accept 1 electron from crystal. Therefore, these impurity atoms here are called acceptor atoms. But in N-type, those impurity atoms were called donor atoms, and here the impurity atoms are called acceptor atoms because they want to accept 1 electron from the crystal. Okay, so you can say in P-type semiconductor, conduction is due to the motion of holes, or you can say P-type is hole rich. As you have seen, the hole is present there. So in P-type, number density of holes is greater than number density of electrons. Okay, and always remember, holes cannot move by itself. Only first the electron will move, only then you can say hole has changed its place, because when electron will leave its place, a hole will be created there. So holes are just changing its place because of the movement of electrons. Okay, so now 4th point says, obviously holes will be majority charge carriers and electrons will be minority charge carriers in P-type semiconductors, because as you have seen, holes were there, right? Now again, instead of having more number density of holes, this P-type semiconductor is also electrically neutral. And how does this happens? Because as I told you, this aluminium accepts 1 electron. So that means when it will accept 1 electron, it will be having a negatively charge. And from where the electron comes, that seat or that hole will be having a positive charge. So negative positive will cancel out. So therefore it will again become electrically neutral. So either you talk about N-type semiconductor or you talk about P-type semiconductor, both are electrically neutral. Okay. Now if we talk about the energy band of P-type, Now see, in this what will happen, as in N-type a donor level was created, but in P-type a acceptor level will be created. So this is your valence band in which electrons are present, and this is your conduction band. So what will happen when you will add any impurity to P-type crystal, or you can say when you will add any trivalent impurity to make a P-type semiconductor, so what will happen, a level will be created near to the valence band which will be having holes, and because these holes want to accept electrons, so it is called a acceptor level. So you can say addition of impurity creates acceptor level whose energy is slightly above the valence band. Okay, so as you can see, this level has energy slightly greater or slightly above than the valence band. Now here comes a very important point. So as you know, because electrons are free to move in conduction band, therefore they constitute to the conductivity. But if you talk about holes, when more holes will be present in valence band, they will also constitute to the conduction. So now if you see clearly, this is the acceptor level. So now only this much small energy is to be applied to move these electrons to this acceptor level. That means when these electrons will move to the acceptor levels, a large number of holes will be created in valence band. So therefore there will be a large conductivity, because only by applying this much energy you can create a lot of holes in valence band. So you can say electrons in conduction band and holes in valence band are responsible for conduction. Okay, so in N-type donor level is present near conduction band, and in P-type acceptor level is present near valence band. Okay, so again I have written same point here, that less energy is provided or required, which will create a large number of holes in valence band. This means again the conductivity is increased by doping, or you can say by adding impurity atom in the pure crystal. Okay, so this was all about P-type semiconductor. Okay, so the next topic is electrical conductivity of extrinsic semiconductors. So in this we will see how conductivity of these semiconductors depends on temperature. So first of all we will be deriving a equation for conductivity, and then we will relate it with the temperature. Okay, so for that I have taken a block of extrinsic semiconductor here, which is having electrons and holes. Okay, let us suppose its length is L and area is A. So as soon as you apply a potential here, what will happen? The electrons that are present here will try to move towards positive potential. So they will be starting moving, like you can say anti-clockwise, or sorry, clockwise, and holes will be attracted towards negative potential. So they will start moving anti-clockwise. So now if you see clearly, there will be an electronic current due to electrons, and there will be a hole current due to these holes. But can you tell me collectively in which direction the current will be flowing if we add both the currents? Because see, if, as you know, the direction of current, or you can say conventional current, is opposite as that of electronic current. So you can say total current will be IE plus IH in the same direction, that is your anti-clockwise direction. Okay, so total current I will be equal to electronic current plus current due to hole, that is IE plus IH. Okay, now I have written one more equation here, which you know already, that electric field can be defined as V by L. This we will be using later. Okay, so now if we use the equation that you have studied in your third chapter, which is I is equals to NEAVD. So if I write due to electronic current IE, that will be equal to NE, that is number density of electrons, into E into A into VDE, that is drift velocity of electrons, and IH will be equal to NH, that is number density of holes, EA VDH. VDH is again drift velocity of holes. Now just put the value of IE and IH in this equation. So that will give you I is equals to EA will come to be common, and you will be left with NEVE plus NHVH. Okay, so I am just writing VDE by VE, which is drift velocity of electrons. Okay, now just take this area component this side, so it will become I by A is equals to E into NEVE plus NHVH. Mark it first equation. Okay. Now, as you know, resistance is defined as rho L by A and electric field is defined as V by L. By using these two relations, we will be calculating the value of I by A. Okay, so now for that, what you do, just divide E by rho. Calculate rho from this equation and divide E by rho. So that will be E is V by L. That is this V by L into rho will be RA by L. So into RA by L. So obviously L will cancel out. So you will be left with V upon AR. Now by Ohm's law, as you know, V upon R is equals to I. So this will be I by A. So that means I by A can be written as E by rho. So just replace I by A by E by rho in first equation. So that means it will become E by rho is equals to E NEVE plus NHVH. Now let us make a small change in this equation number second again. Let us change this drift velocity and we write it in terms of mobility. So mobility, as you again know, is defined as drift velocity per unit electric field. So mobility of electrons will be defined by VE by E, that is drift velocity of electrons upon electric field. And mobility of holes will be defined as drift velocity of holes upon E. From these two, calculate the value of VE and VH. So VE will come to be mu E into E and VH will come to be mu H into E. Put both these values in equation number second. So now that will become E by rho is equals to E into NE mu EE plus NH mu HE. Again, as you can see, E will cancel out from right hand side and left hand side. So it will become 1 by rho is equals to E into NE mu E plus NH mu H. Now 1 by rho, that is inverse of resistivity, is nothing but conductivity. So this equation becomes conductivity, which is E into NE mu E plus NH mu H. So now we can talk about the temperature and conductivity. So now if I increase the temperature, can you tell me what will happen? When you will increase temperature, the number density of electrons and holes will increase. This I have told you earlier also. So as you increase temperature, number density of electrons and holes will increase. That means, as you can see here, if Ne and NH is increasing, obviously the conductivity will also increase for semiconductors with the increase in temperature. Or you can say with the increase in temperature, a large number of electrons will jump from valence band to conduction band, and this will lead to a large number of a large value of current, or you can say conductivity will increase. Okay. So this is the mathematical relation of number density of electrons and holes with the conductivity of semiconductors. Now, if we suppose we have an intrinsic semiconductor, then as you know, in intrinsic semiconductors, number density of electrons and holes is equal to Ni. So just put Ne equal to Nh equal to Ni. So that will give you sigma is equals to E Ni into mu E plus mu H. Now, if it is given, it is a N-type semiconductor. That means it is an electron-rich semiconductor. Number density of holes is very less. So we can nearly put NH equal to 0. So sigma will be E Ne mu E. And similarly for P-type, we can put nearly Ne equal to 0. So this will give you E NH mu H. Or you can say if you have N-type semiconductor, you can neglect the term of NH. And if you have a P-type semiconductor, you can neglect the term of Ne. Okay. Okay, so now there is one question that which current carrier out of electron and hole has high mobility? So the answer to it will be, see, as I already told you, the main current carriers which are moving are electrons. Holes can move from one place to another only due to the movement of electrons, because as soon as electron will go from one place to another, a hole will be created. And mobility is nothing but the ability to move. So therefore, always remember this, electrons have higher mobility as compared to electrons, because electrons are the actual current carriers which are moving. Okay, so electrons have higher mobility as compared to holes. Okay, so after going through today's lecture, you can do question number 1, 2 and 3 from your NCERT book and chapter number 14. Okay, thank you.